Hello everyone, hope you doing good for me. So today I'm going to solve Isi Mmath Subjective 2024 questions. So let's start. So question number 1. Give me the natural numbers. On to linear math. Then let Pi are equal to 1 to P be standard basis. We can find out f1, f2, fp, f g of fi equal to L. Linearly independent. Right? Now define H from Rp to Rm, H of Ei to Fi. Since Ei forms a basis of Rp, that means H is defined for all x in Rp, right? And H is also linear. Now we need to check that H is 1. Okay. Right? Since Fi is linearly independent, so H is equal to H1 implied x equal to y. Hence H is 1. Now is identity on the basis related, tentative identity on the whole space. Right? That means G compose Hx equal to x. Okay. Now come to the part B. F from Rn to Rm is 1 such that 1 linear map such that range of F equal to kernel of G. Let X belongs to, I need to show the range of A intersection range of H. This is trivial. Let X belongs to range of A intersection range of H, which is same as kernel of G. Then Gx equal to 0, Gx equal to 0, Gx equal to 0, right? And H1 equal to X for someone. When G compose Hy, y equal to G compose Hy, because G compose H is identity. which is known as Gx, which is 0. Then y is 0. Y is 0 imply h of 0 is 0, that will imply x is 0. Right? That means intersection is trivial. C. G is an onto linear map, right? Then by first isomorphism theorem, Rn mod cardinal G isomorphic to Rp. Now H is 1 now. P. That means you can identify it as H. Then it will imply that Rn is kernel G plus range H, which is same as range F plus range H. And that time, just by definition, this is to check. Now question number 2. Is the finite dimensional real vector space T V to be a linear map which is diagonalizable? Lambda be the eigenvalue of T, W is the kernel of T minus lambda. Okay, so T V to V be diagonalizable. Okay, let lambda 1, lambda 2, lambda k be distinct eigenvalues. Since T is diagonalizable, that means V is spanned by eigenvectors, right? So let E lambda I become be the kernel of T minus lambda I times I. That means V can be written as direct sum of E lambda I equal to 1 to k. Right? So without loss of generality, let lambda I equal to lambda. So W equal to E lambda. Right? And choose U equal to direct sum of E lambda I equal to 2 to k. Then by definition, since V is spanned by this, is spanned by the eigenvectors, so that means clearly by definition U intersection W is 0 and P equal to U direct sum W. Right? This is done. Now the second part is just a computation. Let x belongs to S of W, apply that Sy equal to x for y belongs to W, ty equals to lambda y. As y belongs to W, S of t of y is lambda S of y, which is same of t of S of y is lambda S of y. T of S of y is basically t of x, which is lambda x, since x belongs to kernel of t minus lambda I. That will imply that x belongs to W. So hence SW is contained in W. Similarly, x belongs to SU, that will imply that Sy equal to x for some y belongs to U, and y can be written Cj lambda j equal to 2 to k S of y, because as y belongs to U, summation j equal to k s of cj vj, sorry, cj vj, where v vj is eigenvector corresponding to eigenvalue lambda j s of vj, right? Now ty equal to t of summation cj vj summation cj lambda j vj j equal to 2 to k, right? Now t of s of y I need to show that t of y, so it's the same process, right? So t of y is this, s of t of y, s of t of y specifically say summation j equal to 2 to k cj lambda j s of vj, which is same as t of s of y, t of s y means t of x, right? Which is same as t of s of x, t of s of y is same as summation j equal to 2 to k cj lambda j s of vj, right? T of s of y, because s equal to ts, right? Which is same as tx equal to summation k vj. Now s of vj belongs to u. S of vj belongs to u, because vj is fj. Okay, s of vj is equal to fj. fj, right? It is lambda j f of j is t of fj, means fj belongs to e lambda j. Okay, it will imply s of vj belongs to e lambda j. That means their linear combination must lie in E. Then tx is to E. Then t is diagonalizable operator, so x belongs to E. Okay, so that means x belongs to sy implies x belongs to su implies x belongs to E. Hence contained in E. Okay, this is just a computational problem, and then I will go to another one problem. Right? R has exactly two non-zero prime ideas. P1 P2 such that P1 intersection P2 is 0. If P1 is not maximal, that means P1 is contained in some maximal ideal, because R is a commutative ring with unity, so any prime ideal is contained in some maximal ideal. And since it has only two non-zero prime ideals, that means P1 is contained in P2, because M has to be P2. Then P1 intersection P2 is P1, which is a contradiction. this will imply P1 and P2 are maximal. Right? P1 and P2 are maximal. It means clearly P1 plus P2 is R, because P1 plus P2 strictly contains P1 and P1 and P2 are maximal, so this has to be R. And by Chinese remainder theorem, R mod P1 intersection P2 is same as R mod P1 plus R mod P2, because by Chinese remainder theorem. Now P1 intersection P2 is 0, because R is isomorphic to R mod P1 and R mod P2. Now P1 is maximal, means R mod P1 is a field, R mod P2 is a field, so R is product of two fields. Ideal of R cross J is of the form I cross J. What is the form I cross J? Ideals of R cross J is of the form I cross J. Hence, K cross K prime has 4 ideals. Zero cross 0, okay, done. Number 4. Let phi from S3 to S3 be a homomorphism. Then kernel phi is normal in S3. The possible kernel identity A3 S3 itself. If kernel is S3, this will imply phi is trivial. Kernel phi is trivial, this will imply phi is an automorphism. You know what S3 is isomorphic to S3. That is quite simple, because you can just take any 3 cycle that will go to again a 3 cycle, because it is an automorphism. And if you are taking any 2 cycle, that will go to again a 2 cycle. Okay. And there is no relation between this. You can just easily manipulate this, and you can just see that that S3 is the automorphism group. So out Sn is Sn x at n equal to 6. That's the standard result. So you can just directly write that. And if kernel phi is A3, then S3 mod A3 is isomorphic to Z2. Okay, so that means G mod ker phi is isomorphic to image of phi. So image of phi is isomorphic to Z2. Now in S3, elements of order 2 are 3. Number of elements of order 2 is 3. So that means only here is isomorphic to Z2, so you can just map the non-zero element will be either either 1 2 this permutation, or 2 3, or 1 3, anything. So that means there are exactly 3. So will imply there are exactly 3 homomorphism, because element subgroup set type subgroup is 3 only. Okay, then total 1 plus 6 plus 3, 10. Okay. Question number 8. X and Y are metric space such that f x to y be a function. Okay. If f is continuous, k is compact subset of x, prove that f restricted to k is defined by that. Right. F restricted to k to y defined by f kx restricted to kx equal to fx for all x belongs to k. Right, is continuous. So let U be any open set in Y. F inverse U is open set in X. F inverse U intersection K is open in K, right? Which is now F restricted to K. This inverse U is basically same as F inverse U section K is open in K. So will imply F restricted to K is continuous. Okay, the second part is quite interesting. First one is trivial. It is given that F restricted to K is continuous for all compact subsets K inside X. Then F is continuous. We need to show. Let's fix a point. Fix x naught belongs to X. To check F is continuous at x naught, it is enough to show for any sequence xn converges to x, f of xn must converge to f of x. Right? This is sequential criteria for continuity. Now, so choose any sequence. Choose any sequence yn that converges to x naught. Define a set A x naught. A is compact. That means F from A to FA is continuous by given condition. Now, FA is what? FA is right. Now, since F restricted on this A is continuous, that means f of xn converges to f of x naught, because f of xn converges to xn converges to x naught, right? On A it is continuous by given condition, so f of xn must converge to f of x naught. So you can do the same thing, do same for any sequence. This will imply that f is continuous at x naught. Right. Next one. So G 0 1 to R is continuous, and f 0 1 to R is a function such that f of 0 greater than 0, f of 1 less than 0, such that hx x plus gx is monotonically increasing. Okay. So we are defining a set A, which is basically x belongs to 0 1 such that f of x is greater or equal to 0, and x naught is supremum of A. And you show that f of x naught is greater or equal to 0. Let f of x naught equal to t strictly less than 0. For any epsilon greater than 0, I epsilon belongs to x naught minus epsilon comma x naught such that f of y epsilon greater or equal to 0. because x naught is the supremum of this set. So if we choose any epsilon greater than 0, we can always find an element y which is lying between x naught minus epsilon comma x naught, such that f of y epsilon can equal to 0, right? Now h of y epsilon less equal to h of x naught as y epsilon less equal to x naught. Okay, so then f of y epsilon plus g of y epsilon less equal to f of x plus g of x. Sorry, f of x naught plus g of x naught. Now f of y epsilon is positive and f of x naught is negative. So we can do this one, g of x naught minus g of y epsilon is greater equal to f of y epsilon minus f of x naught. Now f of x naught is negative, so minus f of x naught is positive, so it is clearly greater than f of minus f of x naught, clearly greater than minus t, which is a positive quantity, right? Now for any epsilon greater than 0, we can find y epsilon such that gx naught minus gy epsilon, this is greater than minus t, which is a strictly positive quantity. This will imply that g is not continuous at x naught, which is the contradiction, because it is given that g is continuous of 0. Hence f of x naught greater equal to 0. Okay. Now come to the part 2. Part B. Prove that there exists a t belongs to x naught comma 1 such that g equal to h of x naught. Okay. So h of x naught equal to f of x naught plus g of x naught, which is greater equal to g of x naught, as f of x naught greater equal to 0. Again, h of x naught is less equal to h of 1 because h is monotonically increasing. And f of 1 is less than 0, this will imply h of 1 is strictly less than g of 1. Hence, g of x naught less equal to h of x naught less than g of 1. And by intermediate value property, there exists a t belongs to x naught 1 such that g of t equal to h of x naught. So we are done. Now third is also easy. So f of x naught we have already shown. We have already known that f of x naught is greater equal to 0. So let f of x naught strictly greater than 0. So f of x naught equal to a is greater than 0. For all y belongs to x naught 1, x naught 1, f of y is strictly less than 0 because x naught is the supremum of that given set. Right? Alright. Now h of x naught less equal to h of y for all y belongs to x naught 1 because it is monotonically increasing. H is monotonically increasing. F of y is negative, so this one is positive, so this one is greater than f of x naught, which is a strictly positive quantity. That means gy minus g of x naught is greater equal to a for all y belongs to x naught, 1. This will imply g is not continuous at x naught. This is a contradiction. Hence, f of x naught equal to 0. Okay, because f of x naught cannot be greater than 0, and we have already shown in the first part that f of x naught is greater or equal to 0. So these are the 6 problems I have already solved here. Okay, only 2 problems are left. I'll solve it later and again upload the video. Okay, I hope this video is helpful, and if you need any help you can ask me anytime. And if you find any mistakes in this solution, please comment below, and if you have any different kind of solution, then also you can verify from me. Thank you.